Okay, so last week we started to talk about phase diagrams. And phase diagrams, just a reminder, tells you typically based on, in this case, for a single material, phase is usually pressure and temperature. We looked at things like this, temperature and pressure, but we will also be looking at materials with two components. So that will be temperature versus composition of the material. And I gave you an example of a binary material that was copper and nickel. Okay, and it looks something like this. So we talked about the phase diagram that had two components, nickel and copper, and that you can have two different phases. You can have a liquid phase or a solid phase. And the reason, this is a very rare situation where nickel and copper are completely soluble in each other because they have very similar sizes in terms of their atomic mass, but also in terms of their atom size. They have exactly the same microstructure, so on and so forth. And so we talked about how to look at something like this and also how to calculate the weight percent of the different phases, right? So we know how to calculate the weight percent of different phases, but that doesn't tell us what the actual material might look like. Okay, so I want to talk a little bit about microstructure. So just looking at the phase diagrams, you know that in this phase you have 100% liquid. In this phase you have some amount of solid and liquid, and then in this area you have 100% solid. But you don't know what the actual material will look like. And so the only way to really do that is by looking under a microscope. Okay, so you look under the microscope, but you don't know if you will get something like, so if you have a material here, so if you have a material that's, say, 35% weight percent nickel, at about 1300 degrees Celsius, you see that you have 100% liquid. So if you look under the microscope, you'll see just liquid. Okay? You lower the temperature to the liquidus line, so that's where the liquid meets the area where you have solid and liquid, so it meets the liquidus line, and you'll see that you'll start to get some small particles of solid that starts to form. And as you lower the temperature, the solid will start to grow. It'll become bigger and bigger. More and more of the solid will also start to form. And then at the solidus line, so where the temperature meets where you have 100% solid and some solid and liquid, that's the solidus line, you will have mostly solid. And then as you lower the temperature some more, you will get completely solid with alpha grains. Okay, so that's pretty intuitive, like that's what you expect. But whether you get big grains like this or small grains, where these are all alpha, you can't tell by looking just at the phase diagram. So what do you think would determine if you get this or this? Because this diagram shows you that if you're somewhere within this region, you should get 100% alpha. And both of these are 100% alpha, right? So what do you think will determine which one of these you'll get? So it has to do with actually kinetics, the rate, how fast you cool something. So the faster you cool, the smaller the grains you will get and the more of them. And the reason is because as you're cooling down, you're getting these small pieces of solid. And if you cool them down really fast, you'll get lots of the small ones, but they won't have time for diffusion to happen for them to grow. So you get lots of small things. But if you cool them down slowly, then the pieces of solid will have time to slowly grow. So the microstructure for the same material at the same temperature, at the same concentration, can look very different. And which one do you think will have a higher hardness and higher strength? Or will they be the same, you think? Right. So the smaller grains will have higher strength, will be harder, and will be less ductile. And that's because the grain boundaries will inhibit dislocation movement. So grain boundaries reduce slip, and so therefore it is more difficult for slip to occur within something like this versus this. Okay, so this will be a ductile, softer material. This will be harder, higher strength, but more brittle material, even though they're at the same temperature and have the same concentration and have the same phase, right? They both have just alpha phase. Okay, so the microstructure also plays an important role when you look at material properties. But something like this is a very rare material where you get 100% solubility. So this following one is actually a much better or more common phase diagram. This is a binary eutectic phase diagram. Have you fill in some of this yourself? So at very high temperatures, what do you think, what phase do you expect would happen at high temperatures? What do you think would be up here? Liquid, okay? And then at very low concentrations of B, where you have mostly just A, you're going to have a solid of A, right? Let's say at 0% B, you expect a solid phase of A at low temperature. So this is alpha. And then at 0% A, you would, or 100% B, you would get a solid phase that's just made out of B, right? And so we'll call that beta. Okay, so alpha and beta are solid. Alpha is 100%, well, it has a microstructure or has a structure of just A. And beta is also a solid and has a structure of the element B or the material B. And you can imagine if I add a little bit of B into A, at high enough temperatures, some of it will go in, right? It will become soluble. But I still have the alpha phase because my structure hasn't changed. And same thing with B. So that's what this phase diagram is telling you. So based on the way I've drawn this phase diagram, which is more soluble? A in B or B in A? Which one is higher? Would you expect to be able to put more B inside A? Or would you expect to put more A inside B? A inside B, why do you say that?
Because the area of beta is bigger.
Right. So the area of beta is bigger. And so it looks like, at higher, you could get higher concentrations of A inside B compared to B inside A, right? And still maintain the same crystal structure. So this is higher. Now, inside this phase diagram and inside this region, what phases do you expect for there to be? So remember, if we were looking at, let's look at here. Let's say we have 25%. Say I draw a line down 25% nickel. At this point, I would have 100% alpha. Up here, I would have 100% liquid. Here, I would have a mixture of some phases, right? And how do I know how much alpha and how much beta? We draw what is called the tie line, right? Remember? We draw a horizontal line across, and the percent of alpha is the tie line, the opposite length divided by the entire length. And then the percent of liquid is the opposite length divided by the entire length, right? So by using the tie line, we could figure out the percentage of the phases, which also tells us by using the tie line, there can only be two phases, two structures in this region, right? If we have three, then how will we use this tie line to be able to figure out how much is the third phase, right? So all of these regions within the phase diagrams have only one or two phases possible. And if you draw a tie line across here, and let's say we would be able to find out the percentage of which two phases in this region, alpha and liquid, right? So in here we have alpha plus liquid. What about in here? And then what about here? Any questions about how we figured out what phases go in the different regions? Because if I drew a tie line here, this tells me I can have the maximum composition of two different kind of phases. And I look to one side, it touches the alpha phase, so I must have alpha. I look to the other side, it touches the beta phase, so I must have beta. Okay, so same here. Go to one side alpha, go to the other side liquid. Here, one side liquid, one side beta. Okay, and then this diagram has something unique called the eutectic point. That's why it's a binary eutectic diagram. So where a liquid goes to two solid phases without going through an intermediate stage where it goes to a solid and a liquid first. Right? So this is my eutectic point. If I have this concentration and I start here, I have 100% liquid. I go down to here, I have 100% solid made out of alpha and beta phases. But if I were here, under the eutectic composition, then I would go from 100% liquid to a mixture of alpha and liquid to continue to lower the temperature to different solids, or two solid phases. So if I'm under the eutectic composition, hypoeutectic, I would go from liquid to alpha plus liquid to alpha plus beta. If I'm above the eutectic composition, hypereutectic, I would go from liquid to what would I get after liquid? If I'm a composition greater than my eutectic composition. Okay? Why do you think that matters? So let's look at something like this. An actual phase diagram. This is a hypothetical one of A and B. We have one of lead and tin. PB is lead, SN is tin. And you have a eutectic composition that occurs at roughly 100 and let's say 183 degrees Celsius. This is the eutectic temperature. And the eutectic composition is 61.9 weight percent tin in lead. So if we have that phase diagram, let's look at the red dots first. At 300 degrees Celsius and 20 weight percent tin. What phases are present on that phase diagram? Liquid, okay. Anything else? No? Okay, 100% liquid. And the concentration of SN in the liquid is, what is the liquid made out of? Lead and tin, how much tin? Of tin, SN. Okay, any questions about how I got this? So I'm looking at that top red dot, right? 300 degrees Celsius, 20 weight percent tin. If I look at that top red dot, it sits inside that liquid region. There's no other phases present, so I know I have 100% liquid. And how much, I mean, if I have 100% liquid, then that liquid must have the same composition as my material, which is 20 weight percent tin and 80 weight percent lead. Now let's look at the second red dot as we lower the temperature. Now we're at 200 degrees Celsius, but still the same composition. So what phases do I have present? Alpha and liquid. How much alpha and how much liquid? Let's say that this point is, what did I use? 18. So let's say that tie line crosses the solidus at 18 weight percent tin and crosses the liquidus at 56. So go ahead and calculate the percentage of alpha and liquid. Anyone come up with a number for the percentage of alpha?
94.7%.
Any questions about how we got this? Do you want me to go over the math a little bit? So this is our tie line right here. Right, a horizontal line that crosses the solidus and the liquidus that goes through the point that we're looking at. Okay, so I have a horizontal line. To figure out the percentage of alpha, I take my tie line and I use the length from the point to the opposite phase. So I go from here to the liquidus. So that length is 56 minus 20. So 56 minus 20, and divided by the entire length of that line. So that's 56 minus 18. If we do the same thing for our liquid phase, so this time I want to know my liquid, so I take my opposite length, which is the part that goes to the alpha. So I have the part on top is 20 minus 18, divided by 56 minus 18, and that should give me 5.3 weight percent. My composition of alpha. What is my alpha made out of? So I know I have in this material at that point I have almost 95% weight percent of my material is a solid and it's alpha, right? What is the composition of my alpha? What's inside? What makes up my alpha? Lead and tin, but how much lead and how much tin? The composition is where that tie line crosses the solidus. So the composition is whatever the composition is right here. So that's 18 weight percent tin and 82 weight percent lead. My composition of liquid is where that tie line goes into the liquidus. So I drop this down here. That's 56 weight percent tin and 44 weight percent lead. It is important for you to know how to read a phase diagram. And this is one of the simplest phase diagrams. So I'll go over another example. So what happens at 150 degrees Celsius, 20 weight percent tin. 100, so that's the third red dot that I have on that phase diagram. So phases. What are my phases present? Okay, so two different solids, alpha and beta. And I tell you my tie line crosses the solvus, the alpha solvus. Solvus is like the solidus, but it's between two different solid phases. So this is my solidus line, and this is my solvus line. My alpha solvus at 11 weight percent tin, and crosses my beta solvus at 98 weight percent tin. So my tie line, this is what my tie line is crossing at point, the third red dot coming from the top. Okay, so calculate the weight percent of alpha and the weight percent of beta. Does anyone have an answer for alpha? What is it?
89.7% of alpha.
And then the alpha here is made out of what? 11 weight percent tin, 89 weight percent lead. And beta here, it's made out of 98 weight percent tin and 2 weight percent lead. One more. Phases present. That's a fourth dot, fourth red dot. Okay, alpha and beta. The tie line crosses the alpha solvis at 5 weight percent tin, and the beta solvis at 99 weight percent tin. So calculate the weight percent of alpha and the weight percent of beta. Okay, what's my weight percent of alpha? And what's my composition of alpha? 5 weight percent tin, 95 weight percent lead. My composition of beta is where the tie line crosses into the beta solvis, so that's 99 weight percent tin and 1 weight percent lead. It is important to be able to do this because we're going to take it one step further now. So if we look at the lead tin structure, what we're going to get is, this is showing you what happens to the material as we lower the temperature. So if you look at this side, the left side, at the top point, you have liquid. And so it's 100% liquid, and this is at some weight percent, let's say 15 weight percent tin. You lower the temperature. Now you're within the alpha plus liquid phase. You're in the alpha plus liquid phase, so you get alpha solids forming inside a liquid. Okay, you're solidifying, you're lowering the temperature, that makes sense. You continue to lower the temperature. Now you're within a completely alpha phase, right? There's only alpha in that region at, let's say, 190 degrees Celsius, point F. And so your alpha phase continues to grow until there's no more liquid, so you get something that looks like this. You lower the temperature some more. Now you have alpha and beta. You already have 100% alpha. Now you need to form beta within that, so you get small pieces of beta that come out of the alpha phase. Can you imagine what might happen if we were on the opposite side? So if we were here, coming down this way. At high temperature, I would have 100% liquid. I lower my temperature, I get into the beta plus liquid range. Okay, so I get beta pieces coming out of my liquid. I lower the temperature some more, I get 100% beta. So the beta pieces grow until it's 100% beta. I lower the temperature some more, now I have little tiny alpha pieces coming out of my beta. So the crystal structure will be like the opposite of this. We'll have like a matrix of beta with little pieces of alpha inside. And that's the importance of a eutectic point, because at compositions less than the eutectic, for hypoeutectic, I get an alpha matrix with beta particles inside the alpha matrix, because I get alpha forming first. And then in my hypereutectic, I get beta matrix and alpha particles. And then if I'm at my eutectic, so that's the graph on your right. So if you look at point H, I have 100% liquid. It crosses the eutectic temperature. So it goes from liquid immediately to two solids, alpha and beta. Both form at the same time. So you actually get layers of alpha and beta. There's no, one phase doesn't have like the matrix and with the second phase as particles, because they form at the same time, so you get layers of alpha and beta. So your microstructure will look very different depending on if you're operating at a hypereutectic concentration or a hypoeutectic concentration. Below, so in this case, the eutectic concentration is 61.9 weight percent tin. So if you have a material that's less than 61.9 weight percent tin, you're going to get one kind of microstructure. And if you have a material that's more than 61.9 weight percent tin, you get a different microstructure. And then you have something exactly at 61.9, then you get a third kind of microstructure. Now let's look at an even more complicated phase diagram. This is copper and zinc. So this is something that's referred to as a binary system with intermediate compounds. So this has intermediate compounds. All right. So you're going to get copper and zinc. And at this portion, you have just alpha. So they've labeled the intermediate compounds for you. You have some place where there's roughly between, let's say, 47 and 50 weight percent zinc. You have a second compound, and that's beta. So that's here. And then you go to a higher region of zinc, and you'll get a gamma, a third. And then even higher, you get delta, epsilon, nu, etc. Okay, so you have several different kinds of single microstructure. So depending on how much zinc and how much copper you have, you get these different kinds of intermediate compounds. What phases do you think exists in here? Alpha and beta, right? Because if you were to calculate the different phases, you would draw a tie line, and that tie line will hit the beta solvis and the alpha solvis. So you know that it has alpha and beta in here. What about up here? What phases do you think you have present in there? Beta and liquid. Up here, above 905, alpha and liquid. Okay, very good. How about here? Gamma and epsilon. Okay. All right, it sounds like you know how to read a phase diagram even when it's complicated. Okay, so that's good. So this is a phase diagram, a binary phase diagram is binary because it has two components, copper and zinc, and it has intermediate compounds. So it doesn't just have alpha and beta, it has other things. So just want to point out one thing. So we talked about the eutectic. There's something else called the eutectoid. And I'm sorry that there are all these unfamiliar words that are very similar to each other. That's just what they decided to use for phase diagrams. So you do have to do a little bit of memorization. A eutectoid is from one solid phase to two solid phases. One solid phase where without changing the concentration, without concentration change, you can get two different solid phases by lowering the temperature. So like something like A goes to B plus C, something like that. There's only one eutectoid on this diagram. I don't know if anyone can see it. It's here. You get delta becomes gamma and epsilon. So delta, without changing the composition, you just drop the temperature, and you go from delta to gamma and epsilon. So that's a eutectoid. And on Friday, tomorrow, we'll talk about why the eutectoid is important.